An inductor is a circuit element that has a self-inductance. This is usually a coil, but we know that every circuit has an inductance, so even a simple wire connected to itself. This also has an inductance, but these kind of circuits have usually a very low values of inductance. So as a result, we usually neglect the inductance of such circuits. But of course, in some cases, on purpose, we place an inductor to a circuit and in such a way that its inductance has a very large value. We are going to investigate these kind of circuits now. So the circuit symbol for the inductance is this, I'm sorry about this. We just quantify this inductor with a single quantity, which is the inductance. If you remember, this was expressed in Henry units, if you remember. And here we are going to start with the simplest kind of circuits that contain an inductor. These are LR circuits that essentially contain an inductor and a resistor. Sometimes we are going to add an EMF device as well. So we are going to discuss the physics of these kind of circuits. What's the function of the inductor in here? What does it do? Why people need inductors in circuits? But before discussing this, we should be able to write down the circuit equations. So as a result, this video is basically, I reserve it for writing down the circuit equations for a circuit that contains an inductor. I'm going to discuss the solutions of these equations in a different video. So let's then start with this. Sometimes the question is like this: there's a switch in here. The switch has been open for a long time. Then at a specific time, at time t equals 0, for example, it is closed, and we are interested in the value of the current at a later time. So in that case, of course, the initial conditions are also determined by this action of closing the switch. So we are going to see that the current is 0 at that time. So that's going to be our starting initial condition. But as we are not going to discuss the solution of the differential equations that we are going to write down, we are not interested within that problem right now. So let me raise this question. So I'm just going to look at any situation where this switch is closed. So let me just connect this part. So I have this kind of a circuit, and I would like to write down a circuit equation for it. As usual, we have a current variable. We have to introduce a current variable. Let's remember that for this, we have to choose a direction first, and then call the current along that direction as I. Again, remember that this direction is up to you. So if you want, you can choose the direction in the opposite way and call the current along that direction as I. That's entirely up to you. So with this too, you can write down the circuit equations. There is no problem with this. Perhaps I can also discuss it like that. But usually people in these kind of situations, they try to choose the direction of the current along the direction of the EMF. So as a result, I'm going to do that actually. So let me erase this thing again and then draw the arrow like that. So the current along that direction is I. Just keep in mind that in principle, that current can be negative, so there is no problem with that. It's just that I have to express the current with a direction, with a chosen direction. So as a result, if you remember Kirchhoff's rules, Kirchhoff's junction rule is satisfied in here. There is no question about what the current is at any point in the circuit. We have to write down the loop rule. So if you remember the loop rule, it was basically saying that when you go around the loop, sum of the changes in the potential is equal to 0. So it's something like that. I'm going to use a highlighter in here. So let's say that you start from here and then go around the loop. You might want to go around along the direction that you have chosen for the current as well, but that's not necessary. You come back to your starting point, and whenever you pass a circuit element, you just write down the change in the potential on this circuit element. All right, that's essentially what we need to do. Unfortunately, we cannot do this. That's not possible. The problem is this. We have a situation in here where the current changes with time. When you close the switch, of course, it just changes from 0 to something else. So as a result, we know that this current produces a significant magnetic field in here, which then implies, let me revert to white, the magnetic field changes. The magnetic field inside, for example, this inductor, perhaps this is a solenoid. We know that there's a magnetic field that changes. And we have seen what happens when magnetic field changes. There's an induced electric field, right? There's an induced electric field produced. And we have discussed this before. We have said that this induced electric field is not conservative. Not conservative means if you compute the work done between 2 points, let's say you just move a charge along some path and compute the work done, the expression that you get for the work done is going to be different if the path is different. Or there's another way of saying it like that. If you just go around the path and then come back your initial point, the work done should be equal to 0. But we have said that this is not the case. If you remember, there was a question where we have a ring inside a uniform magnetic field and the magnetic field was increasing. And there was this question that I asked, what's the potential difference between two diametrically opposite points? And then we have noticed that we cannot answer that question because whichever path we follow, we always get a different answer. So then we decided that this is meaningless. So we cannot define potential in here. We cannot define potential. A potential concept is not meaningful in here. So that's a very important thing. So as a result, since we cannot define potential, then we cannot write down this changes in the potential or things like that. So that's the basic problem in here. Whenever there is an induction, I'm sorry about this, whenever there is a change in the magnetic field, that's the critical point. Whenever there is a change in the magnetic field, the potential concept is not defined, cannot be defined. So as a result, anything that you can deduce from this potential concept, if you disregard that difficulty, then whatever you write down may be incorrect. So as a result, you have to understand the correct reasoning in here. Okay, but it appears that even though you cannot, the potential is not well defined, some people still write down the loop rule and then still get the correct equations. I'm not going to do that actually, but I'm going to say that we can modify the loop rule and then say that in this case the equation is correct. So in that case, of course, I will just refrain myself from defining a potential difference across the terminals of that inductor. So that's the important point. So I'm not going to talk about a potential drop or potential difference on an inductor, but what I'm going to do is I'm going to define an EMF on the inductor. So as a result, let me put a purple color in here. So I'll essentially treat this thing as some kind of an EMF. So I'm going to call the EMF as EL. Or if you want, I can just think of this device as an EMF device with a value of EMF that depends on how the current is changing. That's essentially what we should be doing. So as a result, let me erase everything in here except this loop rule thing. Right? So therefore, I'm just going to say that this form of the loop rule is not valid, so let's just forget about it. But this form can be written down. So if you remember, this is something that we have said. Sum of the EMFs is equal to sum of the current times the potential, current times the resistance, or the potential drops on the resistors. Or you can think of it like that. So let me just write it down like that. So that's basically sum of EMFs, and this is the sum of potential drops on resistors. So in here, of course, you can see that I still try to define a potential outside, at least outside the inductor. So this can be somewhat can be done consistently as long as you can choose a path that doesn't pass over this inductor. That might be possible. So as a result, we don't make a significant mistake by using a potential concept outside the inductor in here. What's important in here is that I have to include the inductor on the left hand side. So this is conceptually more correct actually. So what we do is this. Let me erase again the details in here. What I do is this. So I'm just going to draw this picture again. So this circuit, I'm going to draw it like that. Everything is going to be the same except that I replace the inductor with an EMF device. How do I choose the polarity? Because I have chosen this arrow to measure the current. Since I need to use this current to express the flux on the inductor, I have to be consistent with my direction. So as a result, I'm going to choose the polarity in here is the same as this arrow that I have chosen for the current. So that's the important point. Another thing is this. I know that the flux through the inductor is equal to L times I. So therefore, the EMF on the inductor is equal to, this was Faraday's law, so it's the negative of the rate of change of the flux. Let's remember that in the Faraday's law, there's a minus sign. And we have talked about this thing before. If you choose all the directions consistently, directions to express the current, and the directions for the area and things like that by using the right-hand rule, of course, this equation is correct with the minus sign. So as a result, there is a minus sign in here. That's one of the things that you should keep in mind. So therefore, whenever you take the derivative in here, the inductance doesn't change with time. So therefore, this is the rate of change of the current. So as a result, we have the EMF that I need to use for the inductance is minus L times di over dt. So that's the critical point in here. So what we need to do is to replace the inductor with an EMF device. And of course, for the value of the EMF, just write this expression that you get from Faraday's law. That's essentially what you need to do. And this is also something that's quite easy to remember later on. So there's nothing involved in here. You have to remember just the Faraday's law. This usually is very easy. You just remember that this minus sign is essentially the same as the Lenz's law. It says that there's something opposite to the change. In any case, so also, of course, the flux is proportional to the current, and inductance is the coefficient of proportionality. So that's the only thing that you should remember. So therefore, for this circuit, let me erase this. I'm going to write down the loop rule like this. So sum of the EMFs. So we have the EMF of the battery plus the EMF of the inductor, right? So that's going to be the total EMF. That's the left-hand side. On the right-hand side, I'm going to write down the potential drops. So in that case, of course, this is the same thing as that we have done on DC circuits. So I'm going like that along this direction. Along this direction, the current is I. So I multiplied with R is the potential drop on the resistor. So I just write I times R. Right? Let's remember that on the left-hand side, we have the EMF of the battery and the EMF of the inductor. So both of them should be counted in. I'm not going to ask stupid questions like which one is the real EMF. Well, all of them are real EMF actually, because on a battery, of course, the EMF is a result of some kind of a chemical action. on the inductor, the EMF is produced by this time dependence of the magnetic field. So both of them are essentially mechanisms that give energy to the charge carriers. If you remember, we have defined EMF device as a device that gives energy to the charge carriers. And after that, of course, I don't care how they give energy to the carriers. So as long as they give energy to the charge carriers, they are an EMF device and they are EMFs. So therefore, the EMF of the inductor is also a real EMF because somehow it kind of accelerates the charge carriers on the wire. In any case, we are not done. Of course, I'm going to write down the EMF on the inductor in terms of the rate of change of the current. So the EMF of the battery is constant. So I'm going to write minus L di over dt in here. That's equal to I times R. So basically, this is a differential equation for the current. Current is a function of time. So we have a current expression and the time derivative of the current. So that's why it's a differential equation. All the other quantities that appear in this equation are constant. The resistance, the inductance, and the EMF of the battery, these are constant values. So by using these values, we need to solve for the function I. So therefore, this is the equation that we need to discuss. So we are going to solve this later. So I'm going to, just for fun, look at this other case, what happens in that case. I have said that let me first draw it. I have said that we can choose the direction of arrow for measuring the current in the opposite way. So if somebody has chosen that direction like that and call the current along that direction as I, let me use a capital I in there. So perhaps by doing this, you can compare it with the previous case. So you just compare it with by yourself. So capital I in here is the same thing as minus I of the previous treatment. So as a result, when you replace the capital I with minus I in here, you should obtain the same equations as the previous one. So you can check this actually. So what we do is, of course, we just replace this with this circuit. Let me draw these things as the same. So this is the EMF, that's the resistor. And for the inductor, I'm going to replace it with an EMF device, with an EMF value EL, right? Why I chose that direction? Because this is the direction of the arrow that I'm measuring the current. So everything has to be consistent. So as a result, there's this consistency in here. Sorry about that. This is capital I. So in terms of this, therefore, EL is equal to minus L times di over dt. This is Faraday's law. We have a minus sign in here. Let's just remember that. So how do I write down the loop rule? I don't know. I can go like that. Doesn't matter. Let's just suppose that I'm going like this. So along that direction, the sum of the EMFs is equal to the sum of the potential drops. So I'm actually writing the equation by just looking at the circuit in here. In any case, EMFs. So EL, I'm passing over the EMF device of the inductor in the positive direction. So therefore, this is EL. I'm passing over this one in the opposite way of its polarity. So therefore, I need to write down this EMF as minus E. I'm passing over the resistor in the same direction as that current is expressed. So therefore, the potential drop is I times R. So that's also capital R. Doesn't matter actually. In any case, this is our equation, right? And then I write this equation for the EMF of the inductor. So therefore, this is minus L times di over dt minus the EMF is equal to I times R. Yeah, I suggest that you just check whether this is correct or not. So So there's one last example in here. Of course, I'm not going to solve anything. I'm just going to write down the equation in here. So we have a battery in here, but we have two EMF devices shown in here, but they are in two different branches. So the current passing on this one along the rightward direction is I1, and the current passing on this one along the leftward direction is I2. So I'm going to look at this loop in here. So I'm going to go over the loop like that. So let me put an arrow sign in here. That's the direction that I'm going to go around the loop. You should also, to be able to write down consistent, complete equations, you have to choose a second loop as well. But let's just forget about this. I just want to write down the circuit equation along that loop. So how do I write this thing down? So what I need to do is to first replace this circuit with this one. Battery is as it is. So this middle branch is as it is. So L1 is replaced with a EMF device with a polarity looking towards right. So this is EL1. This is R1. And I'm going to replace the EMF device for L2 with a face looking towards left this time, because the current is along that direction. And then we have R2. So this is EL2, EL2, R2. The current in here is I2. The current in here is I1. All right. So what I'm going to do is, when I'm going around the loop, I'm going to write down the sum of the EMFs and sum of the current times the resistance values. Sum of the EMFs. So let's start with the EMFs. Let me show it with a highlighter. Again, I'm starting from that point and going around and coming to that point, and well, I'll just end up at the starting point, obviously. I pass over the battery in the positive polarity. I pass over the first inductor in the positive polarity. I pass over the second inductor with a negative polarity. So that means when I'm writing the EMFs in here, I'm going to write plus EB plus EL1 minus EL2. Okay. Next, I'm going to write down the potential drop for the resistors. So I'm going over the resistor R1 along the same direction as the arrow of the current. So this is a positive term. I'm going over the resistor R2 in the downward direction, which is opposite to the current I2 in here. So therefore, in the downward direction, the current is minus I2. So that means I have to write this thing down with a negative sign. So let's also write down the right-hand side. So I'm going to write plus I1 R1 minus I2 R2 in here on the right-hand side. Okay, so that's essentially the first point. So that's the complete equation written down. And then what else? Sorry about that. This is the EMF of the battery. And for the EMF of L1, I'm going to write minus L1 times di1 over dt. And for the EMF of L2, I'm going to write minus L2 di2 over dt. And the right-hand side is going to do the same. All right. So we don't have much space left in here. So unfortunately, I'm going to erase something. Yeah, let's just erase the original circuit, let's say. So in that case, what I get would be like EB minus L1 di1 over dt plus L2 di2 over dt. That's equal to I1 R1 minus I2 R2. That's our equation for that circuit.